Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss an important topic about the continuity equation in three dimensions. In our previous lectures, already we have discussed the concept of continuity equation for one-dimensional flow. And now we'll see this equation in three-dimensional object for the three-dimensional flow. Now this continuity equation actually it is fully based on the conservation of mass. And the conservation of mass says that the mass is neither created or destroyed. Okay, it can only we can shift from one space to other space like that. So this continuity equation can be derived by considering a small fluid element. So here I have taken a small fluid element and whose one side ABCD, one side is EFGH that is there. So let consider a fluid element whose length of this fluid element is dx. Suppose this is the dx length in x direction. Okay, this one you can see. This diagram already I have taken from the book. So you can see the length of this fluid element, some arbitrary fluid element we have taken, and for this fluid element, the length of this fluid element in the x direction. In the x direction, it is taken dx. Okay, and similarly, the fluid element length in the y direction. In the y direction, this one. This is our dy. Here the dy is mentioned here. This is in the y direction. So y is here, and this is x, and this is z direction. Similarly, the height, or you can say the length of this fluid element in the z direction, that is dz. This one you can say. Okay, so all these lengths are started, or it is taken from this origin point, this point. Okay, and so these are the, you can say, the length of this. What are the length are there? Dx and dy and dz. These are the fluid length in three-dimensionally with respect to x, y and z direction. Okay, these are the lengths. Now similarly, we can consider the velocity, okay, which are inlet velocity, you can say, of this component in xyz direction. Similarly, you can see this is the x direction, and the velocity for this is u. So u, and for this y direction, you can see this is v. So u, v, and similarly in the z direction, let's consider the velocity is w. So these are the velocity component, or you can say the velocity of this fluid in the xyz direction. So x direction this one, y direction this, and this is z direction velocity. Okay, now the next thing is we need to see that what is the mass of fluid entering to each side. Now this is the fluid element what I have taken. If you see, this is one side ABCD. This is one side of ABCD. Okay, so the mass of fluid element which is entering to this ABCD, okay, how much is there? And similarly, we need to find out what is the mass of fluid which is existing at the other side opposite to this ABCD. So opposite to ABCD is nothing but this one. Okay, this EFGH. Okay, and similarly we need to find out the mass of fluid which is entering at this side, like ABEF, and which is existing DHGC. We will discuss that one later. So first let's see what is the mass of fluid entering ABCD per second. So this one we can write, we know the formula. So mass of fluid which is entering in ABCD surface, okay, per second. Okay, right, per second. So what is the formula for this? We know that rho A B. This formula already we have calculated previously, the mass flow rate. Okay, so rho AV, here we can write rho AV is nothing but the density of this fluid which is coming inside here, and what is the area of this ABCD, and what is the velocity at this particular flow in this direction. Okay, so for this we can write density, we can write the same thing, density rho, and the area of ABCD, area of ABCD. So area of ABCD, you can see what is the area can be taken, and this is the length of this BC, and what is the height of this CD, DZ and DY. So here we can write DZ and dy into the velocity in this direction. Okay, that means in which direction? In direction of fluid flow. So the fluid is flowing in this direction, as we have given this arrow mark, you can see. So this is the surface is there, correct? The surface in this one, the total surface of this. Okay, so at this surface, what is the fluid element is affecting on this? So in this direction, in the x direction, we have taken the fluid velocity is u, so that one we can consider u. So this is the equation for the mass of fluid which is entering to the surface of ABCD per second. Similarly, we need to see what is the mass of fluid which is leaving at the surface of EFGH at the surface. So let me just mark this one. You can see. So this is the EFGH surface. Okay. After entering this side, so at this other side of this fluid surface, we can assume that the fluid which is inlet, like it came inside to this object, the same fluid is supposed to be moved outside from the object along with some extra components. Okay, so let's write down the mass of fluid. Okay, here it is entering, actually not written, but I told entering, and this is leaving. The surface is EFGH per second. Similarly, so here also same formula will be there, rho AV. Okay, but already rho AV, we have already got this one. So this fluid already it is entered at this surface, correct, at this ABCD surface. Now when it's traveling with a length of dx, you can see when this fluid, when the fluid mass flow rate of this fluid, it is already traveled with a distance of dx. So here at this, at this space, there is some changes of, or you can say there is a mass of fluid which is also cross this area, or you can say at this point, at this zone, this box you can see, at this zone also there will be a mass flow rate will be there at this particular zone. So along with this mass flow rate, this also, like the same mass flow rate is crossing this total distance. So there will be a changes of that will be there. So that one we can write in the terms of rho dz and dy and u. This is the mass flow rate which is entering at this ABCD. Now similarly, along with this we can write plus, okay, we can write this one, the derivative of, or you can say del, the same thing what it is entered there. So that one we can write rho u and dx, sorry, not dx, dz and dy with respect to dx along the length of dx. See, this is the mass flow rate which already entered at the surface. Again, the same mass flow need to be crossed this length. Okay, so that one we can just write derivative of the same mass flow rate which is entered here with a length of dx. So this one we can give a square bracket of this. Okay, these two things. Now this is mass of fluid entered and mass of fluid exists at these two surfaces. Then we can write what is the, gain of mass, whether the gain happened or loss happened, what is it? Obviously there is a gain is there, okay, because it came suppose 1. Now it again, when it is existing here, 1 plus some x we got here. So obviously there is a gain in mass of fluid. So you can write the gain in mass of fluid equal to, so we can see how much gain happened here. So the mass flow rate through this minus the mass flow rate of this, then we can get what is the gain of this mass flow rate. So that one we can write what the mass flow rate which is entered here, ABCD surface, that is rho u and dy dz minus, we can write bracket start rho u dy dz plus this equation we can write it, okay, del by del x and du dx dy and dz. Okay, now if you open this bracket here, okay, then these two terms, this one and this terms, you can see both are same, okay, that will be cancelled. So minus if you take inside, then what will be there? That will be minus of del by del x into the rho u, just to keep it in bracket, and remaining terms dx dy d length, these are the lengths are there of this fluid element. This one we can write in this way, okay. So this is the gain in mass of the fluid, how much entered and how much existing. So next, this is for the gain in a mass in the mass of fluid in x direction, we can say, because initially we have taken this one in the x direction. Okay, now similarly we can write the mass of, or you can say the gain in mass of fluid in the y direction. Okay, gain in mass of fluid, gain in mass of fluid in y direction. Y direction, this one you can write equal to, okay, let's see y direction, which one? Now this is y direction. So for y direction, if you see, let me show you here. Now this is y direction object, which is this one, D, okay, CD and GH, CD or HG you can write, this one. This is the, suppose, this surface, and one more surface is there here, this is the surface, y direction. Okay, so the fluid which is entering here, because the y direction we have taken only this way, so what is the amount of fluid, or what is the mass flow rate of fluid which is entering at the surface, and what is the mass flow rate of fluid which is existing at the surface? Which one? This one, AB, and this is EF, this CD, GH, and AB, EF. This is the surface. Okay, so how much mass of fluid which is existing here, which is how much is entering here. So finally you can again similarly find out what is the gain of mass fluid in the y direction. So this is y direction. Similarly, if you see this, if you look this equation, same equation will get in the y direction also. So that one we can write, just will change its direction, del by del y into rho will be there, same fluid is there, so density will be not going to change, but your velocity, if you see in the y direction, the velocity is given v. So here on the place of u we can write v, and remaining things will be as usual same, that is dx, dy and dz, all this fluid element length in the y, x, y, z direction. Okay, similarly we can write the gain in mass, the gain in mass of fluid in z direction. Okay, so x direction we got, now this is y direction, and similarly we need to find out the z direction. Z direction means, similarly you can see, if you see this is the z direction is there. So now if I take, yeah, so z direction means this is the surface, this is the surface which is given, you know, z direction means BC, and this is G, and this is F point actually, which is not visible due to this highlighting, and this upper surface is this one. Okay, so that is z direction, BCGF. Another one is AD, ADEH, or ADHE, this one. Okay, so this is the surface for the z direction. For this we can write again similarly, the minus value will be there, minus del by del z into, similarly here also density will be same, and on the place of velocity, if you see the z direction where the velocity was there, that is w. See, this is the z direction velocity, and y direction velocity v, and x direction velocity u. So similarly we can write rho into w, and remaining things length we can see dx, dy, dz, that is common. Okay, so these are the three equation, or you can say the gain in mass of fluid in the all these three directions. So now next what we'll find out, the net gain of masses. What is the net gain of masses? That we can write net gain in masses. Okay, so here net gain in masses is nothing but if you just add all these things, then we'll get this three things. If we add it, then we'll get the form. So net gain in masses equal to for all this value, if you see, you know, del by del x, dx, dy, dz is common everywhere. Okay, so we can write this one, minus take common, take the minus common, and give a square bracket of this. Now write down del by del x. Here first one is rho u, first one is rho u, plus minus I have taken common, that's why it will be plus del by del y, and this is rho v, rho v, again plus because minus I have taken common, del by del z into rho w, bracket close, square bracket close, then this length dx, dy, dz, that what we have taken. For all these things common we have taken. Okay, so this is the net gain in masses. Okay, so this is the another one equation. Now as per this continuity equation, as I told you, this is based on the conservation of mass. So we can say this net increase of masses, the net increase of masses per unit time, we can say in the fluid element. So let's write down the net increase of masses or mass per unit time, net increase of mass per unit time. Okay, in the fluid element, in this fluid element will be equal to the rate of increase of mass of fluid element, mass of fluid element. So here what I meant to say, the total increase in mass per unit per time, okay, the net increase of mass per time, that will be equal to the rate of increase of mass of the fluid, okay, per unit, or mass of fluid in the element, fluid element. Okay, this both should be equal. So this net gain in mass already we got here. The mass of the fluid we need to find out now. So I'll go to the next slide. Okay, so here we can write the mass of fluid element, that is nothing but we can write here the mass of fluid element. We know this, the mass of fluid element, we can write that is rho into V, because we know that rho equal to mass by volume. So the mass of the fluid element we can write rho into V. Now here volume equal to, we can write the volume of this fluid element, what we can say, the length, the breadth into height. So that one we can consider here. So that means we can write rho into dx, dy and dz. Okay, so this is the mass of the fluid element. Okay, and now see, mass of fluid element. Now we need to find out its rate of increase with time. Its rate of increase per the net increase of mass per unit time. This one we need to find out. So next write down the rate of increase, the rate of increase of this mass of fluid with time. Nothing, just we can derivative of this, derivative of with respect to time. So del by del t rho dx dy and dz. Okay, so you can write this one. You can write rho, just take it outside, del rho by del t, and that is nothing but dx dy and dz. Okay, now this is the equation what we got, that is the rate of increase of this mass of fluid with respect to time. Okay, now these two equations should be same as we as per the definition here. If you see, the net increase of mass flow rate per time equal to the rate of increase of mass fluid in the element. Okay, so now this equation, you can give the equation here. Let's give this is, okay, starting equation not given. Okay, this one you can give the equation 1, this is equation 2, this is equation 3, and by combining this all we got the equation 4. Now next is, this is equation 5. Now this, compare this equation 4 and 5 or equalize these two equations, we can write what we got previously, that is del by del x rho u plus del by del y rho v. See here x is y, here y, sorry, here u, here y, this is v, plus similarly del by del w into rho into w, this is z, del by del z into rho into w. So this is one side into dx dy dz. Okay, this is the equation. Now this equation equal to the equation what we got, the rate of increase of this mass of fluid element with respect to time. So that one you can write again, del rho by del t, again dx dy and dz. Okay, now if you see both the sides, if you see dx dy dz are values are there, so we can just cancel this. Now this minus term, let's take it one side and make it equation 0. That means we can write del rho by del t plus del rho u by del x plus del rho v by del y, okay, plus del rho w by del z equal to 0. Okay, just I have cancelled this dx dy dz in both side, and this minus term I have taken to this side, so this side will be 0. So I have written del rho by del t plus this whole term equal to 0. Now this is your equation 6, and this equation actually, this is the general form, this is the general formula or general form of this continuity equation. Okay, this equation actually we used to call continuity equation for the Cartesian coordinate system in the general form. And this equation, it can be written in different forms, because we know that the fluid flow is in different types are there. Previously we have already discussed different types of fluid flows are there, like steady flow, unsteady flow, compressible, incompressible, uniform, non-uniform, laminar, turbulent, one dimensional, two dimensional, three dimensional, rotational, rotational. So these are the different types of fluid flow already we have discussed. So here also the fluid can be flows like uniformly, non-uniformly, steady or unsteady, compressible, incompressible. So here we need to consider some assumptions. Let the fluid is steady flow. Let's consider the fluid is flowing, which is steady flow. So in this steady flow, we have seen previously our delta rho by delta t will be 0. delta rho by delta t will be 0. If this is the condition, this is the form as per the steady flow, then for the steady flow we can write what is the equation. Just put this value in this equation 6. This term is going to 0. So then the remaining term will be del by del x into rho u. Similarly, del by del y into rho into v plus del by del z rho into w equal to 0. So this is the form of this continuity equation when the flow is steady flow. Okay. Similarly, when the flow is compressible or incompressible, both are there. Compressible, incompressible. Incompressible means your density will be, constant. That means there is no change in density. So for that, again we can write when the flow is incompressible. When the flow is incompressible, then we know that density equal to constant. So in the previous equation, if you see, our density term is there. So take all this density term common and keep it send it to other side. So what we'll get here? So del u by del x plus density I have taken here out, and here also take density out, here also take density out because a constant term, and take a common of this. So remaining term will be del u by del x, and this is del v by del y plus del w by del z equal to 0. Okay, so this is another equation, and this equation is called nothing but the continuity equation for three-dimensional object. Okay, this is the continuity equation for the three-dimensional object when the fluid is incompressible as well as steady flow. Okay, this is the general form. This is the general form of continuity equation, and from this we got these two equations. One is for steady flow, another one is for incompressible flow. So this is the continuity equation. We can give this equation 7, and this is equation 8, and this is for 3D. Similarly, if you want to write the continuity equation for the 2D, then in the 2D case what will be there? This w part will be 0. Or you can write the 2D equation, that is nothing but del u by del x, del v by del y equal to 0. This is for the continuity equation 9. This is for 2-dimensional, and this is for 3-dimensional. Okay, so I hope you understand how to derive this continuity equation in the 3-dimensional for 3-dimensional object, and this is actually the Cartesian coordinate system. Okay, the questions may be given only simple, derive the continuity equation for a 3-dimensional object or for the 3-dimensional fluid flow, or it can be given derive the equation for the Cartesian coordinate system for continuity equation. So I hope you understand how to derive this. If you are having any kind of query regarding this derivation, you can give a comment on the comment box. Thank you all.